this lecture, we are going to now take up the ideas that we developed on the reciprocal lattice in the previous 3 lectures and develop the relationship between diffraction and reciprocal lattice. So, in this Lavey, we had set up these Lavey conditions in the following way, that I have some scattering point A and another scattering point B. There is an incident X-ray point falling on these scattering points, and there is a scattered beam reflected scattered in a certain direction. So, the incident beam is given by the unit vector S naught, the scattered beam is given by the direction is given by the unit vector S. Now, this we also saw can be considered to be a reflection along a certain HKL plane. And we also defined a scattering vector capital S, which is perpendicular to this reflecting plane HKL. This scattering vector, so incident beam makes an angle of theta with the reflecting plane, and it gets reflected from the reflecting plane, and the reflection angle is also theta. Now, the scattering vector itself from the above diagram simply becomes the difference of the 2 unit vectors, unit vector S minus the unit vector S naught. And as we see, that vector scattering vector S is perpendicular to the plane HKL. The magnitude of the scattering vector from the above figure turns out to be 2 sin theta. From there, we got the Lavey conditions. Which is that S dot A equals H lambda, S dot B equals K lambda, S dot C equals L lambda, where vectors A, B, C are the unit cell vectors of the real lattice. Now, since the vector S is perpendicular to the plane HKL and the reciprocal lattice vector R star HKL is also perpendicular to the plane HKL. So, HKL is the plane in real lattice space, and R star vector is in the reciprocal lattice space. Now, the 2 vectors S and R star are both perpendicular to the same plane, which essentially means that the scattering vector S is parallel to the R star vector, which implies that I can write the scattering vector S as some scalar quantity beta times R star, which I can expand it as beta times H A star plus K B star plus L C star. Now, from the Lavey conditions, I can write vector S dot A as beta H A star plus K B star plus L C star dot the vector A. Let us take the dot product of this. So, this is beta times H A star dot A plus K B star dot A plus L C star dot A. Now, from the definition of the reciprocal lattice, B star dot A equals 0, C star dot A equals 0 and A star dot A is equal to 1. Hence, this is equal to beta times H. Now, recall that the Lavey condition S dot A should be equal to H lambda. So, this is equal to H lambda. So, beta H is equal to H lambda implies that beta equals lambda. Therefore, the scattering vector S can be written as lambda times H A star plus K B star plus L C star. The scattering vector S, I can bring lambda on the left hand side. So, S upon lambda equals H A star plus K B star plus L C star, and this is nothing but the reciprocal lattice vector R star. So, this is the reciprocal Now, this actually is another formulation of the diffraction condition. So, this is the vector form of the diffraction condition. So, whenever the Bragg's law is satisfied or the Lavey conditions are satisfied, then it is imperative that the S divided by lambda vector must be a reciprocal lattice vector. Now, this form of the diffraction condition can be set in a frame of reference called the evolved construction, and let us look at what is the evolved construction. So, I have here S, the scattering vector S equals the unit vector S minus the unit vector S naught, these two vectors being the incident and the reflected beam directions, which can also be written by dividing by the wavelength of the X-rays that is used on both sides. So, S bar upon lambda equals S cap minus S naught cap, and again it is the same form S bar upon lambda. If it is becomes the reciprocal lattice vector, then there would be diffraction of X-rays. Again, to emphasize that these two are unit vectors. Now, what we do in this, let us construct a sphere. So, this is where we come to what is called as the evolved construction. So, I have draw a sphere of radius 1 upon lambda. Oh, incidentally, I missed out here. S upon lambda should be equal to the unit vector S divided by lambda and the unit vector S naught divided by lambda. Now, in this sphere, now we put in the incident beam direction. Let me call the center of the sphere as C, and this is my vector S naught divided by lambda. So, this is the incident beam direction, and we mark this point as O. So, CO is the incident beam. Now, let us say we consider a scattered beam at some point P out here. Now, this is represented by the unit vector S divided by lambda. So, Cp is the scattered beam. Therefore, very clearly OP should be equal to the scattering vector divided by lambda. Now, what we do is we take the point O as the origin of the reciprocal lattice. So, now from what we have already learned, for diffraction to occur, the vector OP or the scattering vector S divided by the wavelength must be a reciprocal lattice vector. This implies that this is a reciprocal lattice point at which we have put the origin of the reciprocal lattice. If point P is also a reciprocal lattice point, then OP would be the reciprocal lattice vector. So, this implies that point P must also be a reciprocal lattice point. Then only OP can be a reciprocal lattice vector. So, if there was another reciprocal lattice point falling at some other location, for example, out here, then I will get another scattered beam in this direction. So, this is another reciprocal lattice point, let us say P prime, then OP prime would also be. So, this implies that OP prime would also be a reciprocal lattice vector. So, that is all there is to this evolved construction. And now, what I want to do is very briefly discuss the experimental techniques that are used. It will be a very brief discussion on this, and there will be no details given in this course. Now, experimental techniques for X-ray diffraction, we look at the Bragg's law first. Lambda is equal to 2d sin theta. Now, suppose I randomly place a crystal. So, this is a random position of a crystal and I shoot an X-ray beam of a specific wavelength lambda, let us say perhaps the characteristic radiation emitted by a copper target, copper K alpha, which also happens to be 1.54 angstrom. So, anyway, it could be any other wavelength. So, I shoot at this, we will find that in fact, I can make a statement that we are unlikely to obtain any diffraction if I place the crystal in some random position. And this is simply because probability of satisfying Bragg equation is quite small. So, then our experimental techniques must be such that we are able to obtain not just one or two diffraction, but several diffractions for several HKL planes, then only we will be able to analyze the crystal. So, if one looks at the equation lambda equals 2d sin theta, we find essentially in this equation that there are three parameters. I have lambda, I have theta and I have the interplanar spacing d. Now, for a given crystal, my lattice parameters are fixed, my interplanar spacing is fixed. In fact, those are the things that I want to determine in fact. The parameters that I can play with are wavelength and the angle of the incident beam making with the HKL planes. So, the experimental technique, the experimental method must continuously vary lambda or theta, but not both. If I vary both lambda and theta, I would get a pattern. If I get a pattern at all, it would be impossible to analyze that pattern. So, either I can vary lambda keeping theta fixed with different HKL planes of the incident beam, or I can fix lambda, that means I am using monochromatic X-ray radiation and vary theta. So, in any experimental method, locations of diffracted beam are recorded to obtain what is called as a diffraction pattern, and then it is a pattern that we analyze to understand the crystal. Now, older methods used photographic films to record the locations and chart recorders. Of course, today computers have replaced such techniques. So, there are several techniques and there are several instruments available. I am just going to list down three general methods in which either you vary lambda or you vary theta. So, let me put this down in the form of a table. So, experimental method, and then whether we are varying lambda or we are varying theta, type of sample used, and the major application. One of the very old methods, Lattice method, lambda is varied, theta is fixed, type of sample is single crystal. Application, one of the major application for this method is crystal orientation. So, if I have grown a crystal and I want to find out what is its crystallographic orientation, then I could use the Lattice method. Then there is a rotating crystal method. Here lambda is fixed, theta is variable, but theta is variable in a very limited sense, in the sense that not all possible values. Sample used is again single crystal. This is determining of crystal structures. If you have low symmetry structures, then this method could be quite useful. One of the most popular methods today is the X-ray diffractometer, where wavelength is fixed, theta is variable and all possible angles. Sample used typically is powder or polycrystal. This is useful for identification of different structures that may be present, called as phases. Second, it is for accurate determination of lattice parameter. Now, just a few comments on this. Variable lambda. How do I get variable lambda? I simply use white radiation. So, go back to the X-ray spectrum, simply use the white radiation, you will get a range of wavelengths. Single crystal is used, it is put in a fixed position. Therefore, for the incident beam X-rays, all the HKL planes at some very specific angles. But the Bragg's law can be satisfied in the sense that if it hits one particular HKL plane, look at the Bragg's law. So, theta is fixed for a given HKL plane, its interlamellar spacing is fixed d, it will pick out the wavelength out of all the wavelengths that are available and it will produce a diffraction. So, what we will do now is that I am concluding this lecture here. In the next lecture, we will very briefly look at this Lattice method and the rotating crystal method, and also very briefly analyze these two methods using the reciprocal lattice. Then I will come to the X-ray diffractometer method, which is a very popular and very commonly used method in all characterization laboratories. One would typically find an X-ray diffractometer, which I will explain in a greater detail, and we will solve a few problems regarding analyzing diffraction patterns obtained from an X-ray diffractometer. Thank you.